Finally, we made it. The 10th section of chapter 4. We're there finally at the end. It's called Antiderivatives, and you know that the entire chapter was about the applications of derivatives. So what is an antiderivative? Well, I like to call this a little bit of a segue section. This is going to prepare us for the next chapter, our pretty much last chapter, chapter 5. We will dabble a little bit in chapter 6, just a few sections, but what is an antiderivative? Well, as you've seen over the years of studying math, since early on when you first learned addition, you then got really good at it and learned how to undo it. And the undoing process in math is called the inverse. And that is when we do the reverse. So everything in math, whether it be adding, the inverse operation would be subtracting, multiplying, dividing, squaring, square rooting, logarithms, and exponentials. Now that we've studied for 2 full chapters what derivatives and their applications are, now we're going to talk about how to undo those. And you guessed it, that's right. They're called antiderivatives. Very creative, right? No, not really. We're going to be talking about how to undo the derivative, working backwards, if you will. And that takes us to our first definition, labeling the antiderivative. And so what we're going to actually give, because it's the undoing of the derivative, then what would the antiderivative be? We're going to call it little f of x. So we'll make this make more sense, of course, but when we are talking about the antiderivative, then that big function we know would be the undoing of that derivative, which would just give us f of x. So again, just going the other direction with these things than what we are used to doing, which is just taking the derivative and coming up with that, which is why we spent about 2 chapters, 1 full chapter, learning all the derivatives and all the different ways to take and differentiate a function. And then in the next chapter, chapter 4, which we're wrapping up right now, we learned all the different ways that we can use the derivative and all of its applications. Well, now we're going to be given derivatives, a function that's already had the derivative taken, and we are going to have to go the other direction, called an antiderivative, to figure out what the original function would have looked like. Okay, and we're going to typically know most of these just by looking at them or finding more techniques, memorizing more rules for now working the other direction, the antiderivative or the original function. But there's going to be some that are going to be so complex, those product rules, those quotient, those chains, those are going to be a little bit harder to see and work with. So luckily not in this class, we're just learning the basics in this class of calculus, but more so in the second semester. You will learn different ways and techniques to find all antiderivatives. And hopefully you've noticed that I have stated for every single one of these that there's an antiderivative. Why did I not say the or the antiderivative? An implies that there's more than one, where the implies there's only one. Does that mean that we have to find them all if there's definitely more than one? No, but I will generalize it and talk to you a little bit more about why there isn't just a specific function that gives us the antiderivative. And I know that seems a little weird right now, but I'll make it make sense here in just a minute. So thanks for asking that question. So let's say we had a derivative function already. We'll call it little f of x. And let's say it's 2x. What would we have had prior in order to take the derivative and get that function of 2x? Think about that. Well, it appears to just be a power rule where they brought that power down and then subtracted 1. So we are thinking that the original function, capital F of x, would have been x squared. How do you know if you're right? Take the derivative of that function, and that should give you what you started with. So this is what is called the antiderivative. But is it the antiderivative, or is this just one of many possibilities? Well, what else could I put here that would still, when I take the derivative, give me the 2x? Hopefully you came up with any constant, any number that I put and take the derivative of there is just going to go to 0 and still give us our 2x derivative. So that's why we said that it can be an antiderivative and not the antiderivative. And unless we are given more details, then we will not know what that constant is. They're going to have to give us an x and a y to get our one equation with one unknown to solve for it. So that is what theorem 410 number 2 states, is that if you have an antiderivative of that original function they're calling lowercase f, then the most general antiderivative of that would be this plus some constant, where of course that constant, that c, is some number. So again, anytime we say the antiderivative, we will be giving them the general antiderivative. This can be the derivative for any constant. So just like the derivative was that big, long limit process of our slope, bringing those 2 points together to become one, and we said that that was a mouthful, the derivative was a long word, we just wanted to give a symbol, and you all know that the symbol they came up with was just that, we call it prime, that little dash mark up there. We want to also come up with an antiderivative symbol. And the antiderivative symbol that they came up with is an elongated s we call an integral. Now, it won't make sense to you why it's that elongated s until we get a little bit further into the next chapter, chapter 5, but there is a rhyme and a reason to why it's an elongated s. But you need to know now, whenever you see that symbol, that that is what is called the antiderivative. And we'd also like to name the two different scenarios discussed above. One where it was just the most general, where we have that plus c, and the other where it's not, where we can actually find that value of c, that constant. They're going to have to give us more. So the most general, we're just going to call that the indefinite integral. Indefinite meaning it was not defined where. So it's just the generic, general version, where we're not going to tell you the specific place this is located. And that would look like the antiderivative of our function f of x dx. And we know that it would be equal to the antiderivative of little f is, we're going to call it capital F. Going back to the original function, that if we took the derivative of this, we would get that. And because it's not defined, we will have that plus c at the end, that possible constant, which could be 0, but we don't know unless they give us an initial condition, some x that we could plug into our function and get the original y out. And we call that the initial value problem. Because within that integral, the antiderivative, they're going to give us an initial condition or value where we can then plug in that x and that y to find that one unknown still, called the constant c. So before we get to listing all of the different rules and giving you guys those definitions and theorems, what I'd like you all to do is try to figure out what original function we would have taken the derivative of to get this. So again, we're calling these lowercase f's the derivative of the original, just so that we don't have to have derivatives in our function. Okay, so what would our original function be to get just x? X squared, x cubed, x to the fourth, or in general, x to any power. Go ahead and pause it here, see if you can fill that out, and then we'll go over it. All right, hopefully you were able to get some of those. Now remember, when we took the derivative, when we had a power, we brought the power down and then subtracted 1. Well, because we're doing the inverse or reverse, we're actually going to take whatever power's there and we're going to add 1. And then instead of multiplying, we're going to divide by whatever that new power is. So that is actually going to be, but don't forget, although I can check that this original function is actually the derivative of it, and if I brought this down, the 2's would cancel out and I'd have x to the first. Yep, holds true to what we were given. Remember, I have to put the possibility that there was also a constant with it, unless they tell me an x and a y to figure out what that constant would be. So now that you got that one, if you weren't able to get the others just yet, go ahead and pause it here and figure out what the remaining ones are before I just give them to you. That's what you should have come up with. Again, just adding 1 to the power and now dividing by that power, we would have had x cubed over 3. And if you wanted to check, do the power rule. 3's would cancel, less 1 would give us the x squared that we started with. And of course, all the constants that could possibly be there. And just because it says plus c doesn't mean it's going to be positive. That constant could be a negative. So in general, we say that whatever we have x to a power, to go the reverse or inverse, be called the antiderivative, we would add 1 to the power and divide by that power. And of course, plus our constant. So that is what we are going to now call the power rule for integrals, or the antiderivative. And as long as n is not a -1, because if it was a -1, that's actually 1 over x. That's something much different. What is the antiderivative of x to a power? We would add 1 to the power and divide by the power, instead of multiplying by the power and subtracting 1. We're going in reverse order and adding 1 to the power and dividing by that power, plus our possible constant. Couple of stars around this. You can see it's definitely important, just like our power rule was very important for us when taking the derivative. I'm not going to go through all of these and make you kind of come to the conclusion of what they are. There are some that, again, we should just know, we should recognize, because we spent an entire chapter not only learning them, but then another chapter, this one that we're finishing today, applying them and using them for a purpose. So I'm going to give you a table here where all the derivatives will be on the left and all the antiderivatives, or those indefinite integrals, will be on the right. And the nice thing is you should already have the left memorized. So now we just need to recognize the right. And shouldn't we already have that as well? Yeah, those are just the derivative functions. We just need to be able to work it now right to left, instead of just left to right and taking the derivative. So here they all are in a nutshell. And again, this is a lot of stuff that we've done over the last 2 chapters. All of this on the left, we should already know. Now all we're going to do is throw these elongated s's in front of this side to then come up with the left side by getting rid of the derivative. Okay, so notice, take a look at this one here. Now instead of having the negative there, they're going to just say, what is the antiderivative of a cosecant cotangent? That would be our cosecant. But remember, the derivative of cosecant was negative. So since this doesn't have it, we're just multiplying it and putting it over here. Okay, how about the derivative of e to the u? Well, we knew that was e to the u times du, which the derivative of x with respect to x was just a 1. So it was just e to the x. Well, then if you have the antiderivative of that, you will also get itself, but with that possible constant. All right, so again, this whole right side is just this whole right column. Now we're just going from right to left on all of these without the derivative. Now, the antiderivative. So make sure you grab a screenshot of this and use it for your notes, or let me know and I can print it off for you if you guys need to, or you can do that on your own. Should already have most of these memorized. It's just going a different direction, changes things, makes it a little bit more complicated, because now we got to work backwards. So just to give you an idea of what that plus c represents graphically, visually, take a look at x squared, my original function here. What if I just took it and added 1? Then that would move it up there. Or 2, move it up there. Down 1, down 2. It just moves it vertically up and down. But if I take the derivative of every single one of those, you can see that we would just get 2x. The constants would all just cancel out and get a 0, because the rate of change of all of these is going to be the same. So hopefully that gives you a better idea of why we have to have the plus c, because it could be there, even though you don't see it. So let's talk about, since we're in chapter 4, applications. Let's talk about how this would look if we were to be adding, subtracting, multiplying, or even our position, velocity, acceleration functions, and what their derivatives were. So let's start with theorem 4.10.4. If we knew f and g, we can take their antiderivatives and get little f and little g. Let's say we had f and g, which are the antiderivatives, we'll call little f and little g, and k be some constant. Then we know if we take the antiderivative of f of x plus or minus the other g of x, we can just find the antiderivative of each individually. Capital F, capital G, and of course, still that constant at the end that would disappear if we took the derivative and went that direction. What about a constant? Well, just like when we took the derivative, the constant didn't really matter. It just stayed out in front, and then we took care of business by taking the derivative of that. Well, then same thing with the antiderivative. We will just basically bring that k out in front and focus on taking the antiderivative of little f, which would be capital F. Of course, if that k is out in front and we find that antiderivative, then it's still going to be out in front being multiplied plus our constant. So after all of that antiderivative talk, let's talk about the applications. And we knew that the position function, often given as s of t, that the derivative gave us velocity. And the derivative or instantaneous rate of change of velocity was acceleration, and the rate of change of acceleration was our jerk. Well then now, because we're in the very end of chapter 4, these antiderivatives that we're going to be talking about more in chapter 5, we want to take these types of things and go the other direction. So what would it look like if we took the antiderivative of our velocity? How do we undo velocity? Going a step backwards, we're talking about the position. Or acceleration, velocity, jerk would be our acceleration. So like I said, we worked very, very hard for a very long time on differentiation, but that's because now that we're doing the antiderivative, we're just working backwards. Because if I took the derivative of that, I know I get this. The derivative of that, I know we should know all of these already. It's just going a different direction. We call the reverse or inverse. So that's it. It's all stuff that we've talked about before, but just learning how to undo them so that we're more prepared to do things in chapter 5. So keep working on these things. Again, work backwards. Think about what would I have had to have had in order to, when I differentiate, get that thing that we are now given. And remember, you can always check by simply taking the derivative of whatever you are saying the result is, the antiderivative, to see if you get what you were originally given. Keep working at it, guys. I know it's a little bit weird working backwards, and we've worked really hard to learn all this stuff, and now it's like, now I got to go in reverse. It'll get easier, as always, as long as you put in the effort, time, and mental capacity to actually learn it. All right? I'm here to help. We got our TA. Continue to work and practice this stuff until you feel comfortable. We'll see you at the next one. Chapter 5, Look Alive. Alan, signing off.